Hello, good morning.
Good morning again.
Morning.
Morning, everyone.
We can start anytime now.
Yeah, I guess we can wait a little bit because the initial workshop just went.
Yeah.
ended.
Also, I'll request Adarsh Bidari if things are all in control. Is it going to start right away? Adarsh, can you let us know?
Others just now messaged me that the session is live on YouTube and everything is okay.
Sure, great.
Uh,
Okay.
Hello, can we start the session?
Sure, very much. Yeah, think.
Naga, can you wait? Can we wait a little bit? And we can share the screen a little later because I think Harish sir will sort of introduce the event a little bit.
Okay, sure.
Thanks, Naga.
Right. Welcome to all of the seventh Indian Control Conference. I'm not sure that I'm supposed to do something to get myself onto the main screen. I'm not sure of that. Okay. So welcome all of you to the seventh Indian Control Conference. We are having this conference after another elongated amount of time because of the COVID. Initially, we were to host it in
Sorry, 1 minute. Sorry to intervene. I think the sound is a little low. Can you please speak a little more loudly?
All right. I welcome all of you to the seventh Indian Control Conference. Unfortunately, we had to wait for about 1.5 years before we could get this going because of the pandemic. We were to host this in IIT Bombay in December of 2020. So that sort of got cancelled because of the pandemic, and we were to have this session in 2021. We were hoping to have it live, but unfortunately it could not. As a result, this is the first Indian Control Conference that we are having online. I hope all of you attend this conference and then give us feedback, and we should know then whether we should continue with these online versions or we should go back to the offline now that both these options have opened out for us. Of course, before I let the plenary speaker go ahead, I should thank the huge amount of support that we have got from our sponsors, from people who have helped us get reviews, people who have worked as associate editors and so on, people who have also done the reviewing for us, and also people who have helped us in organizing in various roles during this period coming up to this start of this conference. I guess that is about all that I have to say. So over to Dr. Shovik, who would, I guess, be introducing the first plenary speaker.
Thank you, Harish sir. Thanks for again organizing and putting ICC in place, which is great to have. And again, hopefully there will be some form of physical meeting somewhere in the future as well. That would be nice to physically actually meet people at some point of time. Hopefully the pandemic will get over. Keep our fingers crossed on that. So I'll just introduce Naga. So from MathWorks, and Naga works as a principal application engineer. And his expertise in modeling simulation, real-time system simulation mostly. There's something called model-based design, which you will also hear, kind of modeling the entire system together, how everything comes into the picture in the simulation world. So he's an expert in this area and works with a lot of industries in this domain. He has over 14 years of experience in this area of automotive, aero, renewable energy domains. And the interesting thing is all these domains, the controls get integrated with other type of things, data-driven modeling, something we hear a lot these days, digital twins and how that come into the picture. So those are some of the things Naga will also be speaking about and will be a good thing to understand and listen to. By training, he has a bachelor's degree in electronics and control engineering from JNTU in Hyderabad and a master's in electrical from Texas A&M in the United States. So we're looking forward to hearing from Naga. What do you, Naga? Thanks.
Thank you, Shovik. Thank you very much. Let me just share my screen. Let me know if you can see the screen. Is it visible?
Yes, the screen.
Yeah. Good morning, everyone. Good morning, ICC. It's, as Shovik mentioned, it's always very good to be part of ICC. I've been personally involved, from MathWorks side, part of ICC for the last 4 or 5 years, and I know the energy, that we have when we used to have this physical events, and definitely we will be missing that. But glad to see that we have this online during this tough times, and look forward to meeting you all in person next year. Having said that, I'll be switching off my camera, but again, I'll be turning on when at the end of my talk I can take any questions, and I'll be happy to address any of your queries as well. Great. My topic for today is digital transformation of the industry, new trends and challenges. Right. So here in the ICC, I know a lot of eminent academicians, faculty will be talking. So me coming from an industry, representing an industry, I want to just give a flavor of what's happening in the industry and what are some of these trends and what are some of the challenges that the industry is facing and how we are trying to cope up. Maybe this could be some of the inputs to the research scholars or the faculty to take some of this the research going forward. That's the aim of it, right? All right. I want to first start with a doorbell. Right. It's a simple electromechanical device with a single button that has just one function: what? To ring the bell. But what if you add a camera to it? Now you can see what's at your doorbell before you can answer it. Right. Now, not just the camera, let's also suggest adding a motion sensor. Now, people don't even need to ring their doorbell in order to know when someone is there. Just by the motion gesture, they come to know, they get an alarm and all. Now, how about adding the whole of this, having an access on the cloud, so you can actually see who's at your door even without you being at home, right? That's so now with all of these changes, should you even call this a doorbell anymore, right? Instead of just button to ring, now you have so many qualities in there, so many features in there that we don't even call this a doorbell anymore, right? Well, this is what the digital transformation of a doorbell, right? Digital transformation has completely changed the doorbell from a simple device that notifies you when you have a visitor to a digital security device with a HD video, a motion detection, a smartphone interface that access all the data from your doorbell to the cloud. One company that pioneered in this transformation was Ring. Ring got noticed by Amazon, who purchased the company for a little over $1 billion. Amazon saw a lot of potential and also for additional revenue opportunities far beyond just selling the doorbell devices. There is a subscription plan and a Ring alarm kit you can purchase for additional security. And Amazon saw that it can also provide more secure deliveries if your doorbell is connected with a smart lock, which the delivery person can use to deliver a package into your home and avoid all those things which goes wrong in the first place, right? So who and what were required for this digital transformation of the doorbell to take place? Well, there is a big list. Here is some incomplete list of who, including engineers, IT integrators, algorithm designers, logistics experts, etc. And when you say what, algorithms, data, models, and infrastructure, all of this is hugely required for you to undergo this digital transformation. And of course, this is more than the doorbells, right? It's now digital transformation is across almost every industry. Let's look at few examples. In the industrial automation, where units can be individually customized and then monitored and configured in real time through the use of digital twins, which I'll be talking later in my talk today. For example, in the automotive industry, where we are now seeing fully autonomous vehicles in geofenced applications. If you look at the other energy sector and utilities, where we see the use of predictive maintenance to increase the energy efficiency. Think about the medical devices. You have the smartwatch, a wrist, which can also a smart wristband, which can monitor your emotional state or other health parameters. Managing the upkeep and operation of entire global fleet of aircraft in the aerospace industry, which is one of the huge tasks. And I think this is also going there. The transformation is happening there. Lastly, but not the least, even in the finance market, like the real-time data analytics, we are seeing this transformation happening. So my question, why digital transformation, and why are organizations turning to digital transformation? Basically, there are two reasons. One, to do things better, right? Which is, for example, improve the optimization of it. Number two, add new things to already existing product. For example, a fully transformation of what you offer to your customer that is possibly not available in the market today, like the doorbell example, what we just saw. So what are some of the examples? Like, for example, when you talk about do things better, optimize the design, performance, and operation, predict when the system needs maintenance, and manage a fleet of connected systems, like what we discussed in the aerospace industry, a connected fleet of all the aircrafts and all. When you talk about the broader transformation, going entirely to a new industries, for example, one way to do this is to, say, for example, add wireless access to a product or a system through a smart device, right? That is something happening more in the current scenarios. This can also open the door to expanding for an individual product offering for an entirely platform service that provides unique value to your customer. So instead of a product or a service being an isolated experience, you can also think about as a interconnected with an entire ecosystem of tasks and activities. So the doorbell example illustrates all of this, right? Like both how you can optimize it, also how you can add new things for your own product. And now it's connected to an entire platform for protecting and accessing your home right here. Let's take a simple example of a manufacturing robot. Everything it needs to do is can be completely described using a traditional control systems, right? There isn't sufficient variability or uncertainty that would warrant an artificial intelligence, for example, right? So in this particular case, all it requires is to pick up one particular box from one side of the belt and put it on and place it on the other side. And as I said, it's a simple controls problem. Now, when you look at the same robo in a different atmosphere or different environment like this, where you have a factory floor with numerous robots doing their job and all of them are interconnected. Now think about such kind of a scenario. Would a simple control systems work? Not really. You need to have an add-on along with the controls. So that's this is one of the good examples what we can think about the advent of AI along with the rest of the ecosystem, which is actually giving us a lot of handles and also have a smooth sailing of the complete, in this particular case, assembly line, right? So therefore, too much uncertainty and variable to just schedule such kind of a things. We use AI algorithms to predict when, for example, when the maintenance is required. And this transformation is happening, across the industries, as we just discussed, right? It's happening, for example, what you see for the wind turbines or medicals or automotive industries and going on. So integrating AI has become a priority for companies across today. So we have seen an increase of almost 10 times increase in AI projects in the last 3 years. And this is again, what you're seeing is from the Gartner study of their customers, which shows a tenfold increase. But I would say in spite of having such a humongous craze for the companies to add this, and they are seeing so much of benefits of this, we are still seeing that AI is struggling, right? The adoption is slower than what it could be, and many companies are failing to make their AI projects successful. And you don't have to look very hard to find articles examining the reasons of AI being fail. And for example, I have few things here, what you see from, there are three articles that I am putting in front of you here, which talks about why the AI projects are failing, and they have come up with a lot of reasons. And few of them I'm just trying to collate from all of that, and which could be here is, for example, you do not have a proper data scientist, right? Sometimes these are the skills beyond the teams already have. Or it can also be that you have too much of data. Like a lot of companies are already having lots of data, but they don't know what to do with such kind of a data. Sometimes you don't have the enough data. Like a lot of these startups which are coming with new products, right? They might not have even enough data to to even get into the space of AI. Now, how do you integrate with the rest of the ecosystem, right? And it's just not about your own product. Now you need to, as we just discussed, it has to have an ecosystem which can, not just with your product, but also integrate with the rest of the systems. Like how can I put it on the cloud, or what happens in such kind of scenarios? And probably what is the problem that you're exactly trying to use the AI for? Sometimes we are not even having the right, I would say, the right problem statement. Just because we have an AI, we cannot use it everywhere. So that is one of the key things which we need to be aware of. What is the reason that we are using AI? What is the problem we are trying to solve, which is not solvable so far with the traditional approaches? So, and also, again, this is one study from Gartner again. So they were saying, what are the main barriers for the adoption of AI in the industry? Two things that came out are, one, the skills of your team, and number two is the data quality. right? The skills of your team, a lot of existing engineers may not be having the skill sets of the AI, and maybe also the quality of the data which is coming is not good enough, or you need to do a lot of pre-processing. And not just this, even the McKinsey says that a lot of these teams which are working in an organization are working in silos. Right. So, if, for example, there might be n number of teams, and every team is working in silos, and the sharing of the data, sharing of information across this is also one of the key reasons why the AI projects in such companies are failing. So we really have three main barriers, right? One is the staff skills, one is teams working in silos, the other one is data management. So what approaches have organizations tried in the digital transformation? In some cases, we have seen a big bang approach where the organization build complete infrastructure right from where they're existing to a big jump with large data warehouses or data lakes that we call. And in many cases, the infrastructure isn't what they really need. So this is a very risky approach what people have tried. On the flip side, we have seen a siloed approach where individual groups try to find local optimizations, but end up getting stuck in their obsolete processes when they try to communicate across the groups and handle information across and all of that. The best approach, what we think, would be a pragmatic approach where where you build on the models you already have, build out and leverage the data and analytics that you already have beyond their normal siloed use, right? With each groups connecting to one another, you unleash untapped value of the organization and even realize something which is which you can do a lot of potential with. So here we are talking about a pragmatic digital transformation where you systematically use your data and your models to create and deliver superior value to the organization or to the customers, not just during the development phase or at the point of sale, but throughout the entire life cycle of the product and services, right? So today in my talk, I'll be talking about these two areas of the use of data and the use of models and how they can come together to address such big change that is a digital transformation. Let's look at the data, right? There's a huge data diversity happening, and also it's an opportunity at the same time as a challenge, right? There are numerous sources from where we are getting this data, right? You have the engineering data, the scientific data, the field data, and sometimes you're also getting from the business side, like the transactional data, the business data, right? And all of this data is not perfect. So there's you need to handle such kind of imperfections as well. And now, apart from just that, you also have a lot of data management systems that you can see it here, right? There are so many systems, and you require permissions to access such data. For example, they might be on the cloud, and and this keeps getting bigger and bigger. And what could be the right approach to handle such data? Let me take an example of Gsk Consumer Healthcare, right? So they were using a big batch process data to make products better. I hope you all are aware of this toothpaste, Sensodyne, right? So this is from GSK. It has its own brand value of almost close to $1 billion in revenue, and is growing at a rate of almost 8% a year, right? So one of their R&D scientists is using the insights from this process data to basically squeeze every drop of their efficiency. And he said, as he says in this quote here, the last thing they want to do is build another expensive toothpaste factory, right? So let's look at this, how GSK has looked into this particular problem statement and what they have done. And one of the challenges they have is they have big data and everything is working in silos, right? So now they need to address this across the factories. They have lots and lots of data across the data from the production batches. It's terabytes of data. Let me put it that way. So the first challenge they're trying to address is data which are stored in various silos in separate systems with different logins, access, etc. And for example, here we are talking about the formulations, we are talking about the sales history, we are talking about the production process data, and all other data which typically they might store in the Excel files. So they want to make use of this data and come up with something that can help them solve this issue of data, humongous data, and how can they make some sense of it and extend the efficiency. So they used MATLAB to combine all of such data and clean all this data. They can now match and align all this data, formulations and sales, production together, and find some insights into it. So right from starting, they also started doing some kind of a pre-processing of their data to get insights. Okay, from their production houses, like where exactly it's taking more time. For example, they have this batch process from where they identified 3 important phases: the startup phase, the finishing phase, and in between a phase where they're adding a silica. So they were able to use build an algorithm in MATLAB to sort such kind of a data out and further perform some kind of a statistics to come up with some kind of an insights so that they can improve their process better. So as you can see, it's like it is taking some time for them at the finishing phase, and they want to optimize the process there here. The another challenge which they were trying to address is need systematic views of the data, right? Not just having the data is important, but also having to view, at various phases and as the organization required. So they built a GUI so their process engineers could quickly select and observe data. For example, for formulation, different kinds of formulation combinations, or by various batch numbers, or even by, for example, the operator. So this helped their team quickly iterate, view experiments, and systematically view relevant data. So as a result, so they were able to extract a lot of insights, and then they were able to systematically use their data to improve the complete manufacturing process. They can now answer questions like what affects their process, how is each phase in the process performing, and what happens if they adjust few parameters, right? This helps them to reduce time and time to market of a new toothpaste formula, automated reports for process improvement, and get every step towards the efficiency for their toothpaste plant, so that they can keep growing the capacity without building a new factory altogether again. So what is new to make this easier from the MATLAB side, right? Firstly, we have recently added capabilities like, for example, we support OPC to UA to access data from historians using the secure connection that may now require, right? We introduced a new way of interactivity, working with data called live editor task. I don't know how many of you tried, but I would encourage you to go try this live editor in MATLAB. So these are the apps which you can run in a script for data pre-processing tasks like cleaning the data, retiming, and joining the data. And lastly, the outlier detection that lets you select outlier, where exactly my outlier is, and how can I avoid such kind of things. And we have a new predictive maintenance toolbox to help you design condition indicators and estimate remaining useful life of the machinery, right? So such kind of capabilities that we keep adding to our existing portfolio, which can help the data scientists do a lot better than what they're doing today. But again, this I'm all talking about when organizations have the data, or when, for example, you have all the data. What if you do not have the right data? As we talked about, right? There are multiple scenarios. One, if you have the right data, and number two, if you do not have enough data. Let's look at a scenario when you do not have the right data. We have talked about, let's look at this example where we use simulations to generate a synthetic data, right? Take the case of a hydraulic pump in this particular case. So, it's very important to have a data where there is a leak, right? And now this data is little hard to get from the real plant. So what we typically do is in the simulation, you try to create a scenario, such a leak, what you are seeing here, and then you try to collect this kind of a data. What happens? How is my system responding for a particular failure, like a leak in this particular case, or a blocked inlet? Now I can generate such kind of a data using simulations and use such data for my building my AI models. So it's just not about having the existing data, but use simulations to generate synthetic data that can help you build your own AI algorithms, right? So how do we do it? So for example, typically we have the data from the field equipment or from the laboratory equipment. This is the real data what we are talking about. And from this real data, we are trying to come up with some kind of a predictions, right? Like, various AI methodologies, machine learning, deep learning methodologies. Now that if you do not have the data, we use the synthesized data. Maybe, for example, I create my own set of user-defined data or some kind of a data coming from the environment models, right? So this is something what I can do a synthesized data and club that with the real data that's coming in. And not just that, if we really want to do something a step more, that's where we do some kind of a physical simulation. So we make a replica of our existing plant, right? For example, in this case, a hydraulic pump. Instead of having actual data coming from the hydraulic pump, I create a replica of the hydraulic pump. And what I try to do is I feed in the same information that is happening in the real world, but I try to collect the data from the physical simulation and feed it back. And this goes into the complete data pool, which helps me to do a good prediction model. So what we are doing, that physical simulation of your plant, combining with the rest of the data, real data, is called a digital twin, right? So this is happening right now with a lot of this happening across the industry right now. The concept of digital twin and predictive maintenance, to help organizations come across a lot of overcomes or a lot of hiccups, and they are seeing a lot of value in such kind of an approach. So let me walk you through some of this workflows of how a digital twin works and how our tools from MathWorks will be helpful to you. So in this particular case, what I will be talking about is, say, suppose you have about 50 digital twin models. That means I'm representing a model of my hydraulic pump, and I have like 50 kinds of hydraulic pumps spread across geographically across various countries. What I'm trying to do is I'm creating a digital twin of each and every of my hydraulic plant, right? And each and every digital twin is running some kind of a simulations, maybe 60 simulations at various RPMs, various loads, and various pressure pumps, right? So roughly you might have about, like, say, 3,000 or 4,000 simulations. So in this example, what you see is we are actually talking about a pressure valves for all at 3.8 or 4.0 contour lines respectively. So you can imagine this is a type of information that you can inform the fleet operations, deciding which to move to a maintenance queue, which was pulled on before even significant issues. Where can I apply some more supervisory controls? And how can I predict my RUL or remaining useful life of a particular asset, and etc., right? So basically, what we try to do is we may have n number of hydraulic systems in the field. Those systems are connected to edge called a PLC systems, right? Or it can be any of your embedded target, which streams the data to an OT or an IT layers. OT is operational technology, IT is information technology layers, right? Which will create a digital twin models of your hydraulic operating system. We then are able to take a streaming data to a new level, digital twin data, and start analyzing the data, and basically using your own GUIs, you can try to come up with an optimization based approaches and optimize your complete fleet performance. So let's see how it works across the spectrum, right? So for example, I have to build models and algorithms, right? I can use various approaches like the data-driven approach. I have to do a physical modeling. Maybe I have to tune my models, etc. And I have to reuse a lot of these components. Once I have such kind of a components, I need to deploy them onto an embedded target or some other edge device where it needs to run, right? And then this will be running on an OT and IT systems. This is what we call as a digital twin. So we are basically making a model and running it on an IT and OT systems. And this is connected to your asset management system, right? And whole of this is connected via Kafka. Kafka is actually trying to maintain the complete data synchronization, and here this also helps us to tune our individual digital twin model to a specific hydraulic pump, right? And then that's how you start simulating and creating a digital twins for each and every replica, and you will be analyzing all of these digital twins going forward. And again, you collect the data and you use that data again to further optimize and come back and see, maybe I need to tweak my models, or I need to tweak my algorithms from the data I'm getting. So such kind of a complete process is set right now for use of digital twins to assess future performance of your assets. And this is one of the biggest areas that's happening in the industry where we are in right now. And this is across, when I say industry, what as an engineer coming from a controls background, you can think about building a supervisory control, so building a digital twins and building your AI-based algorithms. Sometimes, now with the advent of reinforcement learning, more mainstream, you can use reinforcement learning to build such kind of systems with the data available and further fine-tune your assets. Right. Such kind of a revolution is happening currently, and I hope a lot of you already are working in such kind of a research areas. So let's look at a step-by-step approach on how do we get to this digital twin, right? The first thing first, we need to model the physical asset, right? That means when I have for example, a hydraulic pump, I need to model my hydraulic pump. Exactly, like okay, what for example, what kind of a valves it has, and what kind of I need to have all the dynamics in place. So that's where the physics-based modeling comes into the picture. So I'm considering the electrical part, mechanical part, the algorithmic part of that helps my hydraulic pump run. And there's a different approach called a data-driven approach, where I already have the data from my hydraulic pump, and I'm using traditional approaches like Kalman estimator, or even the system identification to come up with a data-driven model that can represent my hydraulic pumps. And now with the AI, we can use machine learning, deep learning to represent, come up with a model that represents my system. So there are different approaches, for such kind of modeling of your plant or asset. But which approach to take, right? The question is always a tricky, and this is what I can suggest, right? Now, what factors helps you to choose whether I should go with physics-based or a data-driven or AI-based? The first question you need to ask is, do you have knowledge of the system's physics, or you only have, say, operational data, right? What does your application need? Now, what is your end goal of your application? And coming back to the last important point, the team, what expertise the team has, whether they have expertise in the AI based, or someone has expertise in building the physics based model. So all of these things have to be considered while considering which approach to take to actually build your the model for your asset. So in this particular case, I just want to take a step back. So our approach for digital twins is basically, we see our role as enablers to create, modify, and operationalize any of these forms of models using MATLAB and Simulink. A positive is the foundation skills. A lot of people already have MATLAB and Simulink, right? And this is just a natural extension for a lot of these engineers and scientists to use these tools and take to the next level. And also, digital twin workflows are also a naturally reuse opportunity where model-based design workflows are already existing, right? So people who are into model-based design, they can use this and share this across the people. So we see ourselves from MathWorks as enablers in the digital twin across the workflow, across the spectrum. So using these models, we did create a Simulink model. In this case, we also use some of the Simscape, which helps us to build a physics-based model, right? Create hydraulic pump systems, capturing the motor dynamics, the pump dynamics, and use the valves, pipes, and reservoirs, and the model can be made to look like a real system with the ability to be simulated in time to explore systematic behavior. Now, the next task is to tune the model to real operating system. Okay, I have built the model, but is my model representing the real plant that is running in the real world, right? So for which we need to do a lot of optimization, such that we need to do optimization on so that my model mimics the behavior of the real plant. So first, we need to stream the data from the operating asset, right, into the tuning process. So MathX has support of a variety of common popular protocols like, say Kafka, and to put the processing algorithms on edge systems to PLCs, and do the needed data downstream. In addition, you need to define the tuning methods itself, right? And there are various ways to available for you to do such kind of an iterative optimization-based approaches. So once the tuning algorithm is defined, then pairing it with the model itself, right? That is important. It is converted to a software component that is suitable to be able to execute on a OT system or operational technology system. Let's take a closer look at the tuning, because tuning plays an important role for you to make sure the model is actually mimicking the behavior of the real plant. The tuning method, ability to have access to the data, latest set of tuning of input-output data is very important in this case, right? So the animated figure, what you see here is basically the data that's the measured data coming from the real world, and the simulated data which you are getting from the simulations. And what we are trying to do is we're trying to match the simulation data with respect to the measured data from the real world by tuning some of the parameters in the model, right? So what we call this as a parameter estimation and optimization of the response optimization, which helps you to make sure the model is further fine-tuned and the behavior of the model matches the real asset. So this way we are ensuring that once you have the model that's mimicking the real-time behavior, I can perform a lot of tasks at the model itself and see before I make some changes. For example, I have I have come up with a new software feature that I want to implement on the real asset. Even before I take it to the real machine, I can test on this digital twin and see how the whole system is working, and then I'll have more confidence, and then I can take this feature onto the real world asset. So once a tuning process is defined for one asset, you can actually implement this for the whole of assets in your portfolio, right? So operationally, you'll be triggering the tuning and creating a digital twin and trying to start tuning for each and every asset and putting it back to the model. You have the data, and it's kind of going in a complete sequential fashion. So taking an example in our case with digital twins, we now have the ability to evaluate the operational envelope of each asset as well as the overall fleet. And this can be done by any current operational state of the pumps and systems. This allows to further analyze the results. For example, if there is a no-go operational areas for any given asset based on its operational state and that of a overall fleet. So such kind of an analysis can also lend themselves to do, okay, what to be do and what not to do for your current and the future operations. I can also predict what could be my remaining useful life, or when will my asset will go to will need a maintenance, right? Such kind of things we'll be able to look into. For all the analysis being done, you can also archive all the results. As we create a dashboard for the system operators, they can evaluate the complete operational system and gate action as needed. Lastly, there is a needed testing throughout the design and implementation process. So the algorithms that are put in operation and also the IT OT infrastructure itself requires verification and validation. The algorithms can be tested with expected inputs, while the IT OT infrastructure may require data throughout the sizing and cost estimates, or testing the required connectivity throughout the topology. So what is useful with the digital twin models on hand is that they can also be used to synthetically generate realistic data like what we have seen earlier, right? Into the overall system, and make sure that the first time you test things is not with the real operating fleet. And this is very important, right? Something we do, we create something new, we don't want to test it on the real world so that we might, if something goes wrong, you are actually playing with thousands of dollars of your asset. So creating a digital twin will be a very realistic approach for you to try out new things and test how it works in the real in the scenarios closer to the real world. So let me put it, what we have dealt so far, let me put it, in a context here so that you can understand how and why we use digital twins. We focus today on the various operational tasks of connected systems, speaking about applications like predictive maintenance, digital twins. Important to remember that operational systems are made from products, components, and from system developers, right? The developers have goals that generally translate to both making a better product and making the overall design process better. So digital twins are more broadly digital representation of the product throughout its life cycle, not just in the beginning or not just at the end, but throughout the life cycle. You need to have these virtual representations as early as possible, reusing them throughout the development cycle and also during the end while it's in the maintenance. So most generally, digital twin representation is of a physical or a virtual product is a system. It's a representation of something that is real and or will be real in the future, right? As you can see on the left side, it's when we are still at the requirement phase, we are trying to come up with a product that could be in the near future. Digital twin can also be used something that is ongoing right now as we develop a product, and sometimes during the end of the system where it's already running and we are using the digital twin for the maintenance purposes. And as you can see, this connects the whole of the ecosystem, right from the system requirements till the operations and sustainment. So you can consider this as a digital thread which helps you to perform to fine tweak the requirements or the models or operations across various stages of the product life cycle. All right, so how can we improve a design process and make things better? For example, as I've written down a few steps here, perpetually upgradable systems, the higher performance and resilient systems, lower development and product cost because of this, a complete virtual asset and process creation, continuously validate customer requirements and expectations, and operational feedback to improve the designs and improve the product going forward. And what is a direct value for the customers? It's basically they optimize the operations and productivity, lower operational costs and maintenance costs, and you're coming up with a new product and service opportunities and new business models altogether. So there are a lot of our existing customers who are leveraging this trend of digital twins using MathWorks toolchain. Here are a few examples I've put on the slide. ASML develops a virtual metrology technology with a machine learning algorithm. These are from the systems developer side. As we have seen from the last slide, you can have system developers and system operators. Developers are the ones who are developing the systems and how they are using digital twins like ASML, Schneider, Atlas, Copco, or Lockheed Martin, right? Similarly, if you're looking from the systems operator side, we have our own Tata Steel, who have used this approach to save almost 40% energy on cooling towers, right? We have an example from Building IQ, who provides predictive energy optimization for buildings, and examples from mining and other industries as well. So a lot of people are already using this, and a lot of people are getting into this as well. I just want to say that this is a unique platform. MATLAB and Simulink is a unique platform which is helping powering new applications like be it control systems, right from control systems you perform verification, validation, code generation. What we call this is a model-based design approach. Similarly, if you have lots of data, use machine learning and deep learning techniques, and also signal processing and image processing to perform some kind of a data analytics. And when both these are put together, you are coming up with the new applications, right? And this is what the magic is, and everything can be performed from one single platform. And that's exactly the reason why MathWorks is considered a leader in the Gartner Magic Quadrant for 2020 for data science and machine learning, just because of the platform. It is helping a huge customer base. If I just zoom into this leader quadrant, right, as you can see it, the completeness of the vision, the ability to execute, because we believe this recognition demonstrates our ability to empower teams, even those limited with a limited AI experience. You can support entire AI workflows, not just developing the workflows, but how do you deploy those algorithms onto edge or even to the cloud, right? How can you even tackle the integration challenges and manage risk in designing AI-based AI-driven systems? So why is MathWorks leader in this area? First, as I just said, we have a trusted platforms of MATLAB and Simulink to systematically use data and models. And because MATLAB and Simulink are used in a variety of industries and applications, opportunities abound for groups to connect across organizations to deliver a superior value to their own customers, right? And this can be done throughout the life cycle as you go from system requirements to architecture, design, implementation, testing, and out into the field. With that, I conclude my talk, but before leaving, I just want to keep this in mind today. I would like to leave this thought, right? How can you systematically use your own models and data as part of your product, your pragmatic digital transformation? Thank you again. Thanks for giving me this opportunity, and hope you enjoy this conference, and looking forward for joining more ICCs in the future. Thank you. I'll be happy. I have a few minutes. I'll be happy to take any questions. Can you hear me? Or okay, there is. Okay, it looks like. Shobhik, can you help me with the questions? I'm not able to see. I cannot hear you.
Hello, am I audible now?
Yes, yes, Shobhik.
Okay, sorry, I was speaking. I think there's some issue with the microphone. Yeah, thanks, Naga. I think we can take up some of the questions. So some of them are put in the chat window, but we can take them verbally as well.
Okay.
One question which at the end has come up, but that's a very interesting question, is kind of what is a digital twin? I think one of the slides, slide 49, specifically talks a little in detail about that. So to the person who has asked the question, was that clear when Naga talked about that, or any other specific question? I think what is a digital twin is also kind of dependent on the application bit, like what we want to do with the digital twin, right? So
yeah, maybe I can just give a snippet of that. So any digital twin is like a replica of your real asset, be it your motor or be it your pumps or any of the device that you're working on, a real physical asset. And I want to have a digital replica of that. And when I say digital replica, typically, coming from the controls background, I create my own plant model. But is that the digital replica? Not exactly, right? I have my own physics and I have my own data. But if I just replicate that, it is just a replicate of that. But when I say a digital twin, that is, it is actually behaving how the real asset behaves in real time, right? For example, today, how is my motor behaving? The model should also behave the similar way. That means I need to have give the similar inputs to my model as if I'm giving to the real motor right now. And the performance output should also match with each other, right? It's like a twin of your real asset. That is what we mean by digital twins here.
The other question is deployment easy as compared to Python-based applications?
Absolutely. So we have a very well integrated workflows, where you can take your models and the algorithms And we have this good, beautiful coder products from MathWorks side, which can convert the models into C or C++ code, or even a CUDA code if you want to deploy onto GPUs, right? So we have where you are focusing mostly on development rather than actually writing a code or thinking about the deployment. So I would definitely say it's has a lot of edge over the traditional approaches.
Yeah, I think also just to add to that, there are multiple ways by which you can integrate MATLAB with Python as well. So if there is specifically on this AI, if there is something in the deep learning world like PyTorch, Keras type of frameworks, those can also be brought into MATLAB and the other way around. So that options are there as well.
Sure. Absolutely, yeah.
Some other questions which put some links in the chat window, but Harshad, you had a question on has MATLAB added support for applications other than clustering, classification, for example, libraries for adaptive control or reinforcement learning? Yeah, for reinforcement learning, we are doing a workshop. We had a part of it in the morning, and then there will be a part of it in the second half as well. So there is a specific reinforcement learning toolbox, basically, which does a lot of things in this area. And same for adaptive control. I hope the links help. Yeah, Naga, feel free to add anything on this.
Oh no, I think you're right, Shavik. I think we do have a lot of examples. I think I'm just reading a question from Harshad about support for applications other than clustering, classification, and prediction models. Yes, there are a lot of examples on our website and also with the MathWorks tool chain, especially also using the reinforcement learning. So if you can go through that and let us know if you have any specific questions on any application, we can have offline chat on that. Definitely. I think there's a hand raised from Ramakrishna.
Yes.
Yeah.
So a very,
please speak up, sir.
Yeah, a very general question, maybe naive also. So for a long time, industry used to use these training simulators, right, for their personnel. So what is the little subtle add-on to a training simulator, which will get you can call it as a digital twin? What's the little difference between these two concepts?
Yeah, that's a good question. So when you say a training simulator is basically, like as I said, I have the physics and I have the model replica of my system, but I'm using it just to train my models or anything. The digital twin takes it to the next level where, for example, I have my, say, a motor running for almost 10 years now. Okay, assuming, and definitely during this 10 years phase, there'll be a lot of wear and tear. Right, and now over the periods, the performance also degrades of the motor. Now, when I want to create a digital twin of that, right, I can just create, say, a simple equation-based or a physics-based model of my motor, but the response of this motor, it will be different from the response of the physical asset, which is like a 10 years old. Now, I need to make sure my model is also is like a 10 years old model, right? So that is the key here. So what we try to do is, first we try to match the performance of the real motor versus the model that I have built, so that the performance is almost same. And now when I try to feed in the same inputs to both of these, I should get a similar response. And at that level, once both are behaving same, I can perform any kind of an activities on my model. That is what the idea here. So you are taking it to the next level. The digital twin is like one level next to the digital simulator, what you just talked about. Does that answer your question?
Sure. Yeah. Thanks a lot.
Sorry, I'm not able to hear you. Okay.
Yeah, I think.
Yeah, thanks. Yeah, that answers my question.
Okay.
Amol has put a question in the chat window. Where is reinforcement learning playing an important role in the digital twin technology?
Good question again. So as we can see, right, as we are getting lots and lots of data, we need to make use of this data and come up with algorithms that tune our models, or coming up with algorithms that can mimic a particular behavior or thing, like what we just discussed. I have to predict something happening 10 years down the line. right? So we can start using the reinforcement learning algorithms to help my model learn by itself, right? By providing such data. Okay, now I'm providing all this false data, and how do I, how can I, use this data to learn and come up with an algorithm that I can deploy it so that my algorithm will behave even though my operation is like a very old, or it can, when it faces with a real failure, it can avoid such kind of failures. So you're using such data for reinforcement learning to train and overcome such kind of a scenarios beforehand.
It's kind of like digital twin is sort of the holistic approach, and there can be multiple things inside that. It can be like physics-based classic controls part of it. It can be data-based modeling, reinforcement learning. So all these things can be kind of part of the digital twin concept.
Absolutely, absolutely. Thanks, Shobhik. Yeah.
Vatsal has a question. Is it like modeling in real time? So we're assuming that, is it as in the digital twin is like modeling in real time? Is that the question?
I would say a little closer to the real time, yes, because it has, the model should run in real time. But what we are also doing here is, apart from just real time, this also has to run in the cloud, where you are directly getting the data from the real asset. For example, I have a wind turbine which is in somewhere in the Tamil Nadu region, right? And also have the similar wind turbine somewhere placed in Australia, right? So in real time, I cannot just have that data, copy that data and try to put it in and then start running. That is one way of looking at it. Another way of real time, what I mean here is, I have a digital replica of my wind turbine somewhere in the cloud, right? And I'm getting continuously, this particular model is running based on the data coming from, say, the turbine from Australia or turbine from Tamil Nadu. And this response of this wind turbine on my cloud, the behavior is closely matching my real wind turbine that is placed in Tamil Nadu or in Australia, for example. So think about that. Your models are now running in the cloud and continuously getting the data from the real asset, like a wind turbine somewhere, placed thousands of kilometers away.
Hello.
Yes.
Sure.
Yeah. Hi. I have one a very small question.
Okay.
That is digital transformation and digitalization both are same things or they are different?
As I said, yeah, I would say a little different. Digitization is digital transformation is your
digitization, digitalization, and digital transformation.
May I know what do you mean by digitalization? Then I can say,
I just came across both these words, digitization and digitalization, and that's why I asked. Means, are they? Yeah.
See, again, the digital transformation is, as I told in one of my earlier slides, like, where you're improving the process of your existing system, right? Optimizing your existing methodologies by, going digital a little bit. And then also not just the optimization of the existing process, but also add new features or new techniques or anything, that can also be used. So that is what we mean by digital transformation. Digitalization is, I think, to some part is like, you're converting everything into a digital world. That's what I see. The transformation of your assets or equipment, what we work, right, as engineers, is where the digital transformation comes. So I'm sorry, I might be a little misunderstood about digitalization, but this is what we mean by digital transformation. To improve your existing
that's completely fine. That's completely fine. Thank you.
Thank you very much.
That also clarified a lot. Yeah.
Thank you.
Thanks to everybody who is keeping this nice interactive discussion. Any other questions, thoughts, clarifications? Just feel free to raise a hand or put it in the question answer or chat window.
It says Soumyadeep has raised his hand.
That his question has been answered.
Oh, his question has been answered. Great. Yeah. All right. Yeah. I think if there are no questions, thanks again. Thanks for giving us this opportunity. To give me this opportunity to talk to you on some of these interesting areas of digital transformation and hope you got something out of my today's talk, and looking forward for any questions or any help from MathWorks side in your projects going forward. Please reach out to us. We'd be happy to discuss and help you in your own projects and research work. Thanks again. Thank you, ICC, and and all the best for the entire conference, and all the best for all the participants, and looking forward to meet you soon.
There is one more question.
Yeah, that's a very so somebody. Our question is researchers to study more.
Okay.
I'm putting some links, but yeah, Naga, feel free to show anything if you want.
Sure, we can share that offline. Sure.
Yeah. I guess there are a lot of resources. It depends on what you want to do, because otherwise it will be kind of like bombardment with too many things. So if you can also, I guess, share a little bit more about what you are planning to do, your research topics or any specific course or anything, then we can discuss more about this. But for now, I'm also putting some links in the Q&A section on digital twins. If you want to go through it later on, that's also fine. Thanks again to all the participants, organizers, and friends.
Yeah, I just placed my email address is here. So if you have any questions, you can write to me, or you can write to Shobik. We'll be happy to answer your questions. Thanks again. Thank you very much. Have a great conference ahead.
Thank you.
Thank you.
So thanks everyone for joining. So our next session starts at 11:30. We have two tutorials, one on data-driven modeling and fault detection using principal component analysis, and the other is on foundations of stochastic approximation and reinforcement learning. So see you all at 11:30 in one or the other of these two tutorials. Thanks.